It's an honor to have with us here Dr. Kathy Yelick as a triangle discipline lecturer. Kathy got her PhD from MIT in 1991 and then joined UC Berkeley, where she's now a professor of electrical engineering and computer science. Kathy is also now the director of NERSC, the National Energy Research Scientific Computing Center. Kathy's research covers a lot of areas in high-performance computing, including performance modeling, analysis, and optimization, communication libraries, multiple processors, etc. Kathy is the co-inventor of the UTC language and the titanium language as well. So Kathy's talk today is titled Programming Models for Petascale, and let's welcome the speaker.
Thank you, Jasang. So I'm going to warn you, first of all, that this laptop is fairly new. It came with my new job, and it has a high security protocol, which is going to cause it to go off if I talk too long on any one slide. So let me see if I can keep up with my own slide presentation. And I also want to say that I'm going to talk a little bit about hardware and a little bit about programming languages and software, and touch on some applications, and then also talk about algorithms. So hopefully there's a little bit for everyone here. I don't want the people, if you feel like this is all review at the beginning because you know all about the current trends in hardware, then please stick with me for part 2 of the talk. So first of all, Moore's law is of course alive and well. That transistor density is doubling roughly every 1.5 years. There is some point at which we're going to probably run out of Moore's law as well, but that hasn't happened yet. The real problem, though, is that Moore's law is no longer translating into clock speed scaling. What I'm showing here is a very old slide that many of you may have seen before, which is looking at the trends in power density in processors prior to the multi-core revolution. So if we had kept cranking up the clock rate as we were in the time of the Pentium and Pentium 6 and so on, we were hitting towards some ridiculously high levels of heat inside of the chips. So this is one of the main reasons, in addition to running out of instruction level parallelism, that we have moved towards multi-core processors. So, and the reasons behind this is that the high concurrency systems are more power efficient, so you can have the same performance even if you have, by lowering the clock rate and keeping, and then therefore using less power than if you try to have a higher clock rate. So the basic reason is this formula here, V squared FC, which is the voltage squared times the frequency times the capacitance. And if we increase the frequency F, we also have to increase the supply voltage V, so we have a much more than a linear effect. Whereas if we just increase the number of cores, that's increasing the capacitance, so we get more of a linear effect. So that's the technical reason behind multi-core, and it means that we use less power if we have concurrency, rather than trying to crank up the clock rate in order to get performance. On the other hand, if we try to hide all of the concurrency inside of the hardware, that also consumes power. So things like speculative execution, dynamic dependence checking, and so on also burn power at runtime. So in order to, so the push towards parallelism, and if we push this to discovery of parallelism into the software rather than having it done automatically in the hardware, we do that to save power, and in particular to lower the power density in the chip. So this means that the parallelism problem, of course, now is being handed to the compiler writers, the library writers, and to the application programmers. So a challenge for those of you who are application programmers or library writers is, can you double the concurrency in your algorithms every 1.5 to 2 years? So in keeping with the Moore's law trend, rather than doubling the clock rate, we're going to be doubling the number of cores. So now the challenge for you is not just to deal with dual core or quad core, but to imagine that every couple of years you need to be able to double the amount of concurrency in your algorithms. This is some data that is from Stanford and also some people at Intel and Microsoft, showing a number of different aspects of current hardware trends. The transistor density, there is the green line at the top, which you see scaling in the usual Moore's law fashion. I don't know if I can get my mouse to show up here. There it is. So there's the transistor density. The dark blue curve here is the clock speed, which you can see a dramatic tailing off of the clock speed. This is the power, which is also leveling off. and this is the instruction level parallelism. So this is just kind of putting everything onto one slide to show the problem that we're in right now with respect to hardware and why we have all of this on-chip parallelism to deal with. Now, what does this mean at the large scale? The title of my talk is about petascale or petaflop computing, and the same thing that's happening within a single chip, of course, is happening within petascale systems. And this is some data from the top 500 list, and what you see here is the #1 machine in the top 500 list, the green line, over a period of years. And so that #1 line there is the Livermore Blue Gene L machine, and the red line is the lowest machine that's on the top 500 list. So in order to make it on the top 500 list today, you have to have about a half a teraflop. You have to have about 5 teraflops in order to even be on the list of the fastest 500 machines in the world. And obviously these trends you do not see a flattening off of either one of these trend lines. The #1 machine is rather jaggy because often a machine will sit there for a couple of years, like the Earth simulator or now the Blue Gene systems have done that. What's interesting about this data, and the top 500 data is measured by something called the LinPack benchmark, which is based on dense linear algebra, and therefore measures something that's about as close to the peak performance of the machine as any benchmark that we have around. So it is not very reflective of real applications, but what I think is the most interesting about this data is actually the historical trend that you see here, which is the increasing performance of these, which is kind of reflective of the peak performance. Another interesting observation that Eric Strohmeyer and Horst Simon made is that there's about a 6 to 8 year lag between the top machine on the list and the number 500 machine on the list. Which means that whatever performance we're at in the #1 machine, about 6 to 8 years later, that is going to be the performance of the 500th machine on the list. Okay, so we're pretty close to a petaflop. Question about whether it will be 2008, 2009, somewhere along there. Certainly there are a number of agencies and institutions who are working on putting together petaflop machines in the next year or so. And you can see that trend line actually indicates that we will cross over that petaflop line somewhere around in late 2008 or 2009. And that means that in about 6 to 8 years, assuming these trends don't completely fall over, that we're going to have petaflop machines that will be commonplace in high-end computing. So anybody who has sort of a high-end computing cluster that is one of the top 500 machines in the world will also have a petascale system. And the petaflop in itself may not be so worrisome. What is worrisome is that the number of cores that we're currently using in order to get to a petaflop will be on the order of 100,000 to 1 million, with a Blue Gene type system probably being closer to 1 million cores, a heavier weight system based on, say, a Cray AMD processor or an Intel processor being more of probably in the 100,000 range. So that's a lot of parallelism to find in your applications, and a lot more people are going to have to find that parallelism if we get to the point where there are 500 machines around that have that scale of parallelism. Perhaps even more dramatic is if you look at what a typical desktop has, there's about a 8 to 10 year lag between the 500th machine on the top 500 list and whatever your desktop provides. So this bottom blue line is showing desktop performance. So what this means is that you may have a petaflop machine on your desktop in about 2025. So for those of you who are students, you should be thinking about the fact that in about 2025, you're going to have to be thinking about what to do with a petaflop on your desktop. The question, of course, here is, will anybody care enough to actually build these things? There are also many technical challenges in order to get there. The other one being, can we program something with on the order of 1 million cores for applications that are of broad enough interest to people that they will actually want to use 100,000 to 1 million cores? So I think we need a fundamentally new approach to thinking about this problem of computing in general. We need to rethink the hardware and think from the scratch about from the ground up about what limits the performance. How do we build efficient hardware? Rethink the software towards massive parallelism and eliminating all the scaling bottlenecks in the inside of the applications, eliminating, for example, replication of data structures that cause the scalability to be limited, and even rethink the algorithms. So I'm going to say a little bit about each of these topics. So rethinking the hardware. So a petaflop machine is on the order of $50 million today, somewhere plus or minus, depending on exactly who you buy it from and at what point in time you buy it. So The next thing I want to talk about is good ways to buy a $50 million machine and then throw away your performance somehow by not buying either the right machine or not using it very effectively. So the number one way to waste some of your $50 million is to ignore the power budget. So the power budget is the top concern in hardware design. And as I said before, power density is the limitation within a chip, which has led to multi-core. Energy consumption, though, so power over time, is also very important. It's always been important in handheld devices. So handheld devices today, of course, or even laptops, are designed to be very energy efficient, but especially, even more than laptops, cell phones and so on are designed to be very energy efficient so that they have long battery life. This is increasingly of interest in desktops because, for example, a desktop machine, if you have one of those in your house and you leave it on 24 hours a day, it is likely to be the top consumer of energy in your household right now. So if you're leaving on a high-end kind of desktop right now, that's a very large consumer of electricity in your electricity bill. So these are also soon going to be a significant fraction of the budget in large-scale systems. So if I'll talk a little bit about the amount of power the energy that these systems are going to consume. The one kind of overall knob that we have for reducing energy use is to increase concurrency and try to turn down, as I said, the power consumption. This picture shows chip area rather than power, but on the side you also see the power numbers for a number of different processors. And the point of this is that if you look at the way processors are designed today, we are for the most part designing processors to optimize for serial code performance. That is, we're worried about the fact that we're mostly running serial programs on these processors, and there's a lot of real estate here in a processor like the Power 5, a high-end server processor, devoted to making serial code go fast. So there's out-of-order execution, there's lots of caches, there's other things to try to do speculation and so on. So this is the Power 5 is an IBM processor. So this is the size of the chip, and it's a 120-watt chip, runs at almost 2 gigahertz. And if we instead look at something like a laptop processor, it's a little less than 1/4 of the size, and also consumes significantly less power, about 15 watts. So the area and the power here often are closely correlated. So that's the Core 2 processor that's inside of laptops, and that now we have lost performance. So we've dropped down to 15 watts, but we also dropped down to about 1 gigahertz. Now, inside the Power PC, the IBM Blue Gene machine, which is that #1 machine on the top 500 list, at least in the Blue Gene P installations of that, it is there's a Power PC 450. So there's the size of the Power PC 450, which is now down to 3 watts, and we've lost a little bit more performance. We're down to 850 megahertz. And even smaller than that is the Tensilica processor, which is a cell phone processor, and it is down to 0.09 watts and still is running at a clock rate of 650 megahertz. Now I picked the Tensilica processor here because it actually has a double precision floating point unit on. So it's not completely out of the question that you could do interesting computations on it because it has at least the floating point support that we expect from on the large scale scientific computing machines. The point of all of this is not that we should go build a high-end supercomputer out of cell phones, but that there's something that was done in the cell phone design, which was to design from the beginning for very low energy and very high efficiency, that is not being done in the Power 5. The Power 5 is completely optimized for performance, and it's optimized performance of a single-threaded piece of code, whereas the Tensilica processor is completely designed for low power, long battery life. And so we can try to take advantage of that in building our high-end machines. Why do we care about this if we're building a petascale machine? Obviously, we're not running our petascale machine off of batteries, so who cares what the power consumption is? Well, if we look beyond a petascale to an exascale computer, which people are already thinking about trying to target in about 2018, so about 10 years from now, there are a number of different groups that have looked at this to try to understand what the power of such a system would be. So there was a DOE report called the E3 report, which looked at exascale computing in a number of application areas and extrapolated various hardware trends from today and estimated that such a machine would consume 130 megawatts. Now, roughly speaking, 130 megawatts is about $130 million per year to run the machine. So there's a significant cost here, maybe half that, but on that order, there's a significant cost here for the power budget now that's associated with these machines. There's a study group that I've been involved with called the DARPA Exascale study. This is a much more detailed assessment of looking at what technology would be required in order to get to an exascale. And the estimate that came out of this group, first of all, there was a target put in place by DARPA, which was the machine will be an exascale and it shall run at 20 megawatts. And we tried pretty hard to see if there was a way of plausibly building a machine in 20 megawatts. And I think that people were willing to go with 40 megawatts. 20 is actually quite a stretch still at this point. But the way that you get to even 40 megawatts is with massive concurrency. So you have to, once again, keep the clock rates fairly low. I think it's running at about 1 gigahertz, and you have very high concurrency. And there's concurrency both between the different cores, which we're all sort of familiar with, but also concurrency in order to mask all the latencies in the machine, because the latency across the machine is going to be significant. So latency tolerant is a key piece of getting performance out of this. And the sort of idea then ends up being a billion-way concurrent application. So imagine now taking your application and finding billions of threads inside of it. And I'm also involved in an NRC study looking at the challenges of multicore, which is basically looking at some of the same issues of power that are being done in the DARPA Exascale study group, except that it's looking at it for the mass market of community commercial electronics and commercial computation, and that this problem of power and multicore are not just problems in high-end computing. So another way to waste your money, besides not paying attention to your power budget, is to buy more cores than the memory system can feed. The specific data on this graph isn't so interesting. It was a very simple performance model, but I just wanted to tell you what's in the model to kind of get a sense of how you can tell whether or not you've got enough memory bandwidth on your system. So this is looking at the amount of time it takes over different estimates over periods of time. The x-axis there is years, and this dark blue line right here is looking at the time to the red line here is looking at the time to fill half of memory on the system. So this is looking at making some assumptions about the cache density, the density of caches that are on chip, and then the amount of time that it takes to fill up that cache on chip. And the other lines are looking at the amount of time it takes to compute on that on-chip cache with a particular algorithm. So there's a number of different algorithms here. The one that's here at the top is an n-squared particle method, which is, of course, one of the things that people use in the grape systems and other systems, and even was one of the motivators for the original Blue Gene system. So particle methods that have very high computational intensity. So you get a chunk of data on your on-chip cache, and you do order n-squared flops on it. So you don't get much better than that. The next best thing is you get a chunk of memory and you do matrix multiply on it, and then in that case you've got n to the 3 halves because it's an n-cubed algorithm running on n-squared data. And then down at the bottom you have the performance, the amount of time it takes to do a stencil operation, so nearest neighbor relaxation on a mesh, or some kind of a matrix vector product, which has a very low computational intensity. So maybe 2 floating point operations for every word of data that's in the cache. So the point of all of this is that whenever these lines cross underneath the time to fill memory, you cannot mask the cost of the memory latency because you don't have enough bandwidth. You cannot double buffer and keep your memory unit completely saturated by overlapping all the memory time with computational time. You don't have enough computation to mask the memory time. Just sort of an aside here, I hear a lot of applications, people talking about the bandwidth limited, my code is bandwidth limited, etc. And John Shelf and the rest of his group at NERSC actually looked at this question in some detail with some applications, some large scientific applications that are generally thought in many cases to be bandwidth limited because they do not run at a high fraction of peaks. So these are applications that, unlike the LINPACK benchmark, these are running at maybe 5 to 10% of the peak performance of these, even on a small machine. And it's a set of applications across a number of different application domains, from fusion simulation, biology, astrophysics, and so on. So what's being graphed here is the total runtime for running one copy of this application code, that's the blue bar, and 2 copies of the application code on a dual processor machine, that's the red bar. And so if the memory system was was not a limiting factor, you would see that these 2 bars would actually be identical. And if the memory system, if the memory bandwidth is a limiting factor, if you've already, for example, saturated your memory bandwidth with one of the cores, then when you try to run a second copy of the code on the second core, your running time is going to go up. And you do indeed see a tiny bit of slowdown by running 2 copies of the code, because they are contending for resources, both on-chip cache and also the memory bandwidth off-chip. But it's a much smaller factor than it would be. It's certainly much less than a factor of 2. So certainly one of the cores here is not saturating the memory bandwidth. So even though most of the application scientists would have told you, if you'd asked them, that their application was already limited by memory bandwidth, even when it was just running on a single core. So we looked at a different problem, which is much easier to understand than these complete applications. And this is work that Sam Williams has been doing, looking at sparse matrix vector multiplication. So sparse matrix vector multiply, if you're not familiar with it, it's not too important, except that it has a very low computational intensity. You've got a matrix, you read a non-zero, you read one of the matrix entries, and you do 2 floating point operations with that. In addition, there's some metadata overhead to store the matrix structure. We don't need to worry too much about that, but at best it has 2 floating point operations per 8 bytes of data that you're reading, so 2 bytes per word. And so it should be bandwidth limited on any of these machines that we have today. So we looked at, so the question is, if you were going to go and buy a machine for the purpose of doing sparse matrix vector multiply, what would you do? What would you buy? So there's 3 possibilities we have up here: the Intel machine, AMD machine, and an IBM processor, the IBM cell processor. So the Clovertown has a peak performance of 74 gigaflops. So you say, well, you know, matrix vector multiply is doing floating point operations. Maybe what I want is a machine with a lot of floating point operations. You may say, well, I want one that has a lot of memory bandwidth. The memory bandwidth numbers here are not very different. So there's a slight difference here. The cell processor has about 25.6 gigabytes per second as opposed to 21.3 on the other 2 processors, but there's not a huge difference in memory bandwidth. So maybe there's a slight advantage to the cell processor, although it only has 14 gigaflops of double precision floating point unit. As many of you probably know, the cell processor is sort of hampered in its double precision floating point unit because it doesn't fully pipeline the interface. So, well, if we run an implementation of sparse matrix vector multiply, once again, this is an algorithm chosen to be very memory intensive, memory bandwidth limited, and also, by the way, spends most of its time just reading the matrix, so it's really bandwidth limited rather than latency limited. It is running at only a gigaflop on the Intel machine and just about 600 megaflops on the Optron machine. There is no such thing as writing naive code for the cell processor, so that's why you don't see a performance number there. You have to go to a lot of work to write code for the cell processor. So what is the efficiency we're getting? We're getting about 1% and 3% respectively. That is relative to the peak performance of these. So what if we do a lot of work to optimize the code on both the cell processor and also on the other machines? How well can we do then? And the answer is we actually, and I'll talk a little bit more about this later, do something called automatic tuning, and we get up to 1.5 gigaflops and almost 2 gigaflops on the 2 kind of traditional multi-core, traditional processors, and but you get over 3 gigaflops on the cell processor. So the automatic tuning there was very important to getting performance, not just on the cell processor where we might expect it to be hard to get performance, but actually on the cache-based machines as well. So it was not obvious from the beginning, but the kind of best machine, best processor to build your sparse matrix machine out of, if the only thing you care about is doing sparse matrix vector multiply, which, by the way, I have to say is only about 3 lines of code if you're writing it in C or Fortran, and therefore is not something you would probably buy a whole machine to do. You would buy a cell processor if you didn't care about the programming overhead. So why is the cell processor so efficient? And the reason is because it has latency hiding through software-controlled memory. So rather than using caches to do latency hiding and prefetching, it actually has a DMA mechanism, a direct memory access mechanism that you can use in software to explicitly move memory up and down the memory hierarchy. That is, from off-chip DRAM up into what's called the local store, which is like a cache but is completely under software control. And this is a little micro benchmark called, which we call Stanza Triad, that shows you the difference in performance between a number of these other processors on the left, the Opteron. It's actually got an old Itanium on there, a G5, and an old Pentium 3, and then on the right-hand side, the cell processor. So what is this benchmark doing? It is streaming through memory, just reading through memory in unit stride order, and then does a jump. Okay, and so what the x-axis here is in both of the graphs is it's the length of that unit stride run. So if the length of the unit stride run is very short, the shortest it gets, by the way, is one cache line. So you read through a cache line and then you jump kind of randomly to another cache line, and then you jump again to another cache line. So on the, so you would think that because we're reading even in the smallest case, we're reading the cache line, shouldn't the memory bandwidth be flat as long as you're not wasting any of that cache bandwidth? And the answer is on the old Pentium 3 system, which didn't have any prefetch mechanisms, you did indeed get flat performance. So it doesn't matter how long your stanza is, as long as you use up your whole cache line, you get maximum memory bandwidth out of it. It is also, by the way, true on the cell processor, and we're showing the performance with a number of different SPEs, but in each case the performance is flat, so it doesn't matter how long your unit stride run is, because you're doing that with DMA operations. On all the other processors, though, because they're relying on prefetch in order to saturate the memory bandwidth, you have to have a very long unit stride run before you actually get close to the peak bandwidth. So the flat lines that you see up here are the peak bandwidth numbers that you would get out of the stream benchmark. So this is the number for the G5, and you can see that you need to have a stanza length of almost 512 words before you get pretty close to the peak bandwidth. So that's a very long unit stride run. Imagine an application, how many of your applications actually go through 512 words before they do something else in memory, and that's a pretty high run to rely on the prefetch engine. Itanium had an even higher number here that you needed to get to. So what's the conclusion from this? That the cell processor with its explicitly managed memory hierarchy actually can give you much better performance than just a cache-based system with prefetching if you're willing to go to the effort of programming it. Okay, so it's a big caveat there, but it is the case. What's another good way to waste your money if you're buying a supercomputer? Well, one of them is to unnecessarily synchronize your communication. Most large-scale scientific codes today are written with MPI, a message passing layer, using two-sided communication. That is a send-receive model of communication. Now, each transfer in a send-receive model has a synchronization event tied with it, which is a message receive, whereas one-sided communication avoids this. And these performance graphs show you the difference in both latency and in bandwidth for doing two-sided versus one-sided communication. So the red bars are MPI, two-sided communication, and the blue bars are one-sided communication. So the left-hand graph here is latency. So notice the latency is noticeably lower for the one-sided communication GASnet than for the two-sided, whereas the bandwidth, now this is for, by the way, modest-sized messages, 4 kilobyte messages, the bandwidth is higher for GASnet than it is for the two-sided MPI. So one-sided, what this says is that one-sided communication is faster than two-sided communication, which is what almost everybody is using today in their scientific codes. They're almost all using two-sided communication. So why is that? Well, here's a little cartoon to try to explain what the reason is for the performance difference. It is not because, by the way, all of the people that implemented the MPI layers didn't know what they were doing and there was some optimization that they were missing. It's actually because there is a fundamental difference in the interface between one and two-sided communication. So when you're doing a send-receive, which is a two-sided communication event, it looks kind of like this. You've got a message ID, and you've got some data that you're sending. You send it off into the network. It goes in the network interface on the other side. And somehow you have to match this message ID with a message ID that comes from the application program that's running over on this side. So there is required in the interface some communication here between the host CPU and the network interface. Now, if you're on a really good network, and you have a really good application programmer, the application programmer will have done what's called pre-posting their receives. So you post the receive long before the message is ever going to come in. That means that we already know what the mapping is between the message ID and the address where the data is actually supposed to go. If you're on then some fancy hardware, that information, that mapping between the message ID and the address gets downloaded into the network interface. That, by the way, doesn't happen on very much hardware, but things like Quadrix will do that. And the message gets matched inside the network interface and gets written into memory. So there are cases where the machines have optimized this path for two-sided messages, but for the most part, the fundamental point is that it required some communication with the application programmer that was not part of transferring data. So one-sided messages instead, what it encodes is an address and a data payload. So this data payload is the same, and it's not. What's important about this is that a lot of network interfaces, any network interface that has RDMA support, so including things like InfiniBand, can pick up this kind of a one-sided message and directly write it into memory without bothering the host CPU. Okay? So there's a reason why one-sided communication is faster than two-sided, and one of the things that we want to do is to avoid slowing down our applications by over-synchronizing things, and this is one of the ways to do it. Okay, so we want to rethink programming models from the lessons that we've learned from hardware. One of the things is we want to redesign them for massive amounts of concurrency, for latency hiding, and for some control over locality, which was what we learned from looking at the cell results. So we really have to have some control over the memory hierarchy. So parallel software is still basically an unsolved problem. Most parallel programs are written either in a message passing layer with most commonly MPI, or they're written in some kind of a shared memory model with OpenMP, Threads, or Java. Now, the problem is that these two things tie together two different notions. One of them is how you are going to communicate between them, that is, by doing two-sided communication versus reading and writing data. And the other question is, who controls the data layout? And so only with MPI do you get layout control, and only with OpenMP or Threads do you get the kind of efficient one-sided communication that avoids this synchronization. So these partition global address space languages are trying to take the best of both worlds. That is a global address space, so you can name any piece of memory across the whole system. You can get an address for it, and you can directly read and write that memory across the entire system. And however, you have the control over the data layout that you need from MPI. So it's like MPI and having control, but it's like shared memory and having both flexibility to describe parallel data structures and the ability to directly read and write into them without interrupting the processor on the remote side. So here's kind of a summary of some of the other features of these partitioned global address space languages. So it's an explicit parallelism model. It is not automatically parallelized by the compiler. It has this global address space, as I talked about. The address space is logically partitioned. So you can take a partitioned global address space model and run it on a shared memory machine or run it on a cluster connected together with some kind of a network. And in either case, the fact that the data is partitioned, and in case of a real hardware shared memory system, you may ignore that partitioning in the implementation, whereas on a cluster, that would be very important to getting performance. You get performance transparency and the ability to tune the performance in these languages. So there's some, the languages, there's three of these languages that have been around for quite a while, almost 10 years. One based on C, which is UPC, a language that I've worked on, CoArray Fortran, which obviously is based on Fortran, and Titanium, another language that I've worked on, which is based on Java. And there's also a set of high productivity computing systems languages from a DARPA program, HPCS program, that has a similar model of the data, but actually has a different kind of execution model with more dynamic parallelism. And I'll say more about that in a minute. So this is the cartoon of our partitioned global address space. There's a partition here for each of the threads or each of the processors. So normally you run one thread per processor in this model, and that each one of those threads has its own local variables, which are down here in the private space. So those would be things like stack variables. And then the heap variables and the distributed arrays and so on are allocated up here in the yellow part of the address space, which is the shared part. And notice that you can have pointers that point all the way into other processors' parts of their shared part of their address space, not into their private part, but into their shared part of their address space. And there's two different kinds of pointers that may be a little bit subtle here, but there are what are local pointers, which are these narrow pointers, like the L pointers in this case, and there are wider pointers, which are the global pointers that are the G variables in this case. And to give you a little bit more concrete idea of what happens in the implementation of these languages, if you implement these languages on top of hardware shared memory, there's no distinction between local and global pointers. If you implement these languages on top of a cluster, then a global pointer turns into a processor ID and a local address on that processor's memory. And when you read or write to it, what happens is a message gets generated, a one-sided communication event gets generated in order to read or write the remote data. So that's why there's two different pointer types. There are, in these global address-based languages, there are ways of declaring both private and shared data. There are a number of differences across the languages, and I'm certainly not going to try to give you a language tutorial here today. All of them have the ability to do distributed data structures, so distributed arrays, local and global pointers, which allows you to build linked data structures and so on, and all of them allow you to do this one-sided communication at the application level. So something as simple as an assignment statement into an array, if X sub I happens to be remote, that will turn into a remote write. Or if Y sub I happens to be remote, it will turn into a remote read, or a pointer dereference on either the left or right-hand side. In addition, something that's important for performance in all of these cases is the languages have some kind of bulk communication or bulk data transfer support. Memcopy is the analog to the UPC, to C's memcopy operation, library operation, and there's various versions of that that are provided in UPC. Titanium, because it's built on a language with real built-in data types, has its own multidimensional array type, and I'll say a little bit more about that in a minute. And from that we build distributed arrays, which are actually very powerful. CoArray Fortran also has distributed arrays. And by the way, CoArray Fortran, they are working on putting into the current Fortran standard. John Mellor-Crummy actually just sent me mail this morning that I haven't had a chance to read with some comments on the current version of the CoArray Fortran language documentation. UPC is not being considered yet for inclusion in the ISO-C standard, although it is in the GCC front end, and it is also in the EDG front end, which is used in a lot of commercial compilers. So it's kind of gotten to be popular enough that it is in some of the standard compiler front ends. All the languages also have the ability to do various kinds of synchronization, global barriers that stop the world, locks, memory fences, and so on. And at least in the case of UPC and Titanium, there's the ability to do collective communication where you do something like broadcast a value or reduce over an array of values. So why are these PGAS languages interesting for multicore? Well, they're a very good fit to shared memory machines because they directly use the read and write support that's provided by hardware shared memory. There are, in the current UPC and Titanium implementations, both of them are implemented on top of POSIX threads, so it's directly using that hardware shared memory support. If you were saying, well, what are they competing with? In the shared memory space, what UPC and Titanium and CoArray are competing with are OpenMP or some kind of thread library, POSIX threads or Java threads or whatever. The difference is that the PGAS languages have locality information, and I think that although today you may be able to get by without that on multicore, and I would say may with a lot, sort of in quotes, as the number of cores grow, I think locality is going to be increasingly important, even if there is hardware support for shared memory. We certainly saw this and see this today on machines like the SGI Altix, which has hardware support for shared memory, but because it's physically distributed, you really do want to write applications that have control over their memory layout. And I think that this model, although it's not quite a match for the cell architecture right now, that is something with a local store, could be extended to give you that kind of control that you need to move memory in and out of from DRAM into the local store. So in UPC right now, or these other languages, you move data sideways between the different processors. What you need in addition is something to move it kind of up and down vertically from the off-chip memory into the on-chip memory. So it's still a useful model, and DMA is exactly the way you do that. Direct memory access is the way you do that on the cell processor. So that's why these PGAS languages are good for shared memory. What about for clusters? Well, they're a good fit for these distributed memory machines because they use the fast one-sided communication. And in particular, what our implementation of UPC and Titanium use is a communication layer called GasNet. And it's also used in the RICE implementation of the CoArray Fortran compiler as well. And the competition, in this case, which is much stiffer competition, I would say, is to message passing programming in MPI. The PGAS languages, the partition model can still scale to certainly to hundreds of nodes. We've done a few experiments on thousands of nodes, but and I think there's no reason that the PGAS language can't scale to arbitrary number of nodes. One thing that I didn't explicitly say that I should say now is that we never cache remote data inside of the PGAS implementation. So this is what makes it much more scalable than a real hardware shared memory or even software, say DSM sort of implementation, is that you can go and access data remotely, but it's not automatically cached for you locally. And if you want to make a copy of it, you make a copy of it and you manage that copy yourself. So that's where we get the scalability from. In terms of ease of use, this is an argument, and I'll say a little bit more about it in a minute with respect to the titanium language, but it's hotly debated in terms of the productivity of these various languages. But I think there is an argument that says that the ability to build shared data structure is really valuable and very expressive and is helpful in a lot of applications. I was talking to, I think, Xiaosang about the BLAST application where you've got a big data set and you're trying to access that data set, or something like a ray tracing algorithm where you have a scene and you might want to do some kind of almost random access of the scene. The ability to put that data structure in shared memory and just access it when you need to is very powerful and makes it easier to write the programs in some cases. I just wanted to mention that the performance advantage that I told you before, which was the one-sided versus two-sided, and this is just another graph showing over message sizes. This is on an InfiniBand network, how the performance, the GasNet performance outperforms MPI, and there's actually almost an order of magnitude difference between the N1/2 number, which is the message size at which you get half of the peak bandwidth of the machine, between these two layers. So there is a big difference in the performance, at least for these mid-range message sizes. When you get to a large enough message size, both of them will top out at the same place, because at some point you will be limited by the hardware. And I just want to reemphasize, this is not, they didn't implement it very well. It's because MPI requires that you do message matching, in some cases tag matching and so on, which slow down the implementation, and you have to synchronize. So there are more semantics associated with MPI. But this also corresponds to performance advantages at an application, or at least algorithmic level. So an important algorithm in a lot of scientific applications is a 3D FFT. And without trying to give, once again, a full tutorial of a 3D FFT, I'll just say that you do it by doing FFTs in each of the local FFTs in each of the rows in each of the 3 dimensions. So so the way you do that is, imagine that your cube of data has been sliced into slabs. Just for simplicity, we'll put it into slabs across the processors. Each processor owns a set of these planes of the FFT. And what you do then is you do FFTs in the 2 dimensions that you own locally in each one of your slabs, and then before you do the FFT in kind of the wrong direction, you do a big transpose of the data. And it turns out that from both performance modeling, algorithm analysis, and something like the log-P model, and also in practice, that experimentally, it's better to do this transpose than it is to do all those little 1D FFTs with the data laid out the wrong way, because you want to send a few big messages rather than doing these little messages across the FFTs. So we looked at the one-sided and two-sided model for doing this FFT computation that includes the transpose, and we actually looked at 3 different algorithms. The first algorithm is called the chunk algorithm, and this is the sort of conventional MPI program, or good programming practice, which is to send as few messages as possible and to make them as large as possible. Well, that is, you send the same amount of data in all 3 of these algorithms, but you take that data and you pack it into the largest possible message to avoid sending messages, because messages in MPI are expensive. So the chunk algorithm says, wait until I've finished my FFTs in both dimensions of the plane, and in fact I've finished all of my planes, and then pack together the messages. So in this case, the data, so for example, all of these blue rows at the top are going to go to the same processor. So I wait until this processor has finished all 4 of these planes, pack together the blue stuff, and send it off as a single message and unpack it on the other side. The second algorithm says, well, wait just for one of the set of rows that are in one of these, one of the planes to be finished, that's going to the same processor. So take all the blue rows, send those as a single message. So in this particular picture here, this processor would be sending 4 messages per remote processor rather than just 1 message for each other processor. And the last algorithm is called the pencil algorithm, which seems kind of crazy, but you actually just do, you've already done the FFTs in the columns, and as you're doing the FFTs on the rows, as soon as you've done one of the rows, you immediately send that row to the processor that owns it. It turns out that this maximizes the overlap of communication and computation. You start sending the data earlier, and you spread it out with more computation mixed in between, and it also matches pretty well the natural data layout, which gives you certain advantages in the local memory system. This is the performance for those 3 different algorithms written in both MPI and in UPC, which uses one-sided communication. The blue bar there is the chunk algorithm. This is, by the way, the standard NAS, if you're familiar with the NAS benchmarks, FT, so a 3D FFT benchmark, which is in the NAS benchmark suite. The only thing we did to it is we improved its performance a little bit by replacing the serial code with a library called FFTW, which is a highly optimized FFT that sort of self-tunes the FFT for the machine. So that blue bar in the y-axis here is megaflops, so up is good, and this is the megaflops per thread, just so we can show it easily on one graph. The processor count is down here at the bottom, and there's a few different networks that you're seeing here, MirrorNet, InfiniBand, and 2 different Quadrix networks. The chunk algorithm is the slowest of the 3. The next best, the MPI algorithm, so the orange bar is the best of all 3 algorithms written in MPI, and the best algorithm for MPI is always the slab algorithm on these machines. You can't afford to do pencils, because in pencils you're sending little tiny messages and that's too expensive. On these machines, the best algorithm for UPC is always the pencil algorithm, because it maximizes overlap and takes advantage of the memory layout in the system, and it outperforms in the MPI implementation in all cases. So that says that one-sided communication is also an advantage even at the application level. Yes.
Can you also compare that to one-sided MPI?
We have not compared it to one-sided MPI, and I'll tell you the reason. First of all, because it would be some work to go and write the code, but the real reason is because most of the MPI implementations are not well optimized for MPI. So I don't think it would actually look very good for MPI.
They're probably not.
Right, but let me say that the conclusion from this is that if you had a well optimized MPI one-sided implementation, I think it would perform as well as ours does. So it's not a criticism of MPI one-sided. There are other criticisms of MPI one-sided having to do with how usable it is, but. Right, but I think that you'd probably get the same performance if you implemented it well. So, are these just toy languages? These PGAS languages, and I want to just give you a little bit of information about titanium, so you can get a sense of where some of the productivity advantages in terms of code size come from. Because I think it really comes a lot from the array abstraction. So one of the main features of titanium is the array abstraction. It's a multidimensional array construct. It's very similar to what you might see in MATLAB or even high performance Fortran or something. You have explicit index sets that you can pass around. You can do things like slice arrays. You can take intersections of index sets. I think is actually more powerful than most those other languages. So a common thing that you may want to do if you have a grid-based computation where you're doing something like nearest neighbor relaxation on a grid is you have 2 grids that logically are next to each other in space, but they both have a little bit of extra data in them called the ghost region around them, so that you can fill in the data in the ghost regions and then just do computation locally. And the ghost region filling in the ghost regions can be kind of nasty code to write if the grids are not all uniform. And even when they're all the blocks are all the same size, it's still getting all the indices right is a little bit tricky. So in something like titanium, all you do is you allocate these in a global index space. So the index of this array and this array actually overlap right here. So this might be element 9, 9 in both cases, even though it's very close to the left edge of that pink array. And then when you need to fill in their ghost regions, you just say copy one array into the other one, and the titanium implementation automatically figures out what part of the index space do they overlap and copies just those data elements, in this case the little green region that's right here. This is especially useful if you have irregular sets of grids around, that is an adaptive mesh algorithm. You place bits of mesh around at different spots where there's more interesting things happening numerically in say a fluid domain, and then you have these little patches you have to do these kind of ghost region updates on, and it makes that kind of code much simpler because you just say copy all of the pairs of grids if you want to, and it'll just copy the right things. And this gives you some idea of the programmability advantage. Now, I hate to use line counts, but it's very hard to do a productivity experiment with a piece of code as large as this one. So this is an application, a Poisson solver written with adaptive mesh refinement that was done by Tong Wen, who was working in Phil Colella's group, and a comparison to that same algorithm written in the Chombo package, which Phil has been working on for a number of years. So the Chombo package is written in C++. They use Fortran for the inner loops because they don't trust the C++ compilers, and I think our experience indicates that for multidimensional arrays, they're probably right. It uses C++ because they have these hierarchical trees of grids, if you will, and they didn't want to program that in Fortran 77. And they use MPI then to do communication. So, and the line count here on the right is for the C++ MPI code, and is broken into different pieces, parts of the application code. So this is the array library you build up in C++ here. There's some AMR, adaptive mesh refinement data structures, and so on. And then this is the elliptic solver, the Poisson solver there at the top. This is the line count for titanium, which you can see is significantly, almost a factor of 5 lower than the line count for the Chombo version. Now, you might object and say, yes, but that's because you're counting all those array libraries, and those array libraries are reusable across a number of different places, which is true. I think what this is doing is saying, let's take things like array libraries, push them all the way into the language implementation runtime in the compiler, where the compiler can optimize them, you can implement them once, and you can fix the bugs once when you find them. And you do find bugs in there, and they get fixed once, not just once for this application and then again for another application. This is the speed up on a modest number of processors here, and the point of this is a little bit small, is just that the performance you get on these two codes is actually very similar. So there's not a big performance advantage in this case, but there is also not any significant slowdown. The other large application that we've worked on in titanium is a heart simulation, which is based on a method called the immersed boundary method, where you're modeling a set of elastic structures within an incompressible fluid. The method was developed by Charlie Peskin and Dave McQueen at the Courant Institute at NYU. It has some complications from parallelism because you have basically two data structures. One data structure of particles, which are connected together in these little linked structures. For example, this is a heart muscle fiber, and that muscle fiber is going to contract and expand depending on what phase of the heartbeat you're in. And then there's a fluid, which is represented as a regular fluid mesh. In this case, it's shown in 2 dimensions, but it's actually 3D in the code. And each one of these points, at every time step, you have to both spread the forces out to the surrounding points, which is what's shown here by these arrows, and then also later in the computation, after you've done a Poisson solve on the fluid mesh, you pull the forces back. So it's sort of a scatter-gather style communication pattern. So this is the lines of code count in this case between a Fortran implementation and a titanium implementation. So it's only about a factor of 2. However, the Fortran code contains no parallel code. So this is just vectorized code written for a Cray C90. It doesn't have any MPI or anything like that in it. So I think it's still a fairly significant difference. There's some speed up numbers. These are because we didn't have an MPI implementation compared to. There's no comparison. This is just showing that the performance of the titanium code is indeed dropping as we add processors. Here's a little bit of the visualization of the heart, just to show you that you can actually do real things in titanium. I won't say a lot about this since this is not a talk about heart simulation. You'll notice that the heart looks kind of funny there at the beginning of the heartbeat. By the way, you're seeing one heartbeat just repeated over and over again in the visualization. This was something that we reproduced in titanium, but it was originally done in the Fortran code. You may notice a couple of odd things. One is that the heart seems to move around a lot. That's because it's just basically a heart sitting in a box of fluid, and as it contracts, it does indeed move around a lot. In fact, one of the bugs that we had in the code that took us a long time to figure out was that it moves around so much it actually moves off of the edge of the fluid. The fluid is toroidal, so it wraps around, so it all works correctly as long as you've wrapped everything around, and we were missing some wraparound code, but so the heart actually flew off the edge of the fluid domain and therefore exploded. So that's a little bit of titanium. I think I want to skip now this last piece, which is looking at matrix factorization in UPC, and talk a little bit about some algorithms, because I think the other thing that needs to happen is we need to rethink the way in which we're writing software and also the way in which we're writing algorithms. So we're designing algorithms. So one of the things that we are doing kind of the moment unrelated to the UPC and titanium projects is looking at program synthesis techniques. This is Ross Bodick's work, who's looking at something called sketching. And the basic idea in sketching is that you write a simple piece of code as a specification, and then you write a more complicated piece of code, which is your idea for the optimized version, but you don't necessarily fill in all the pieces because, for example, some of the index bounds may be complicated, and then you run a theorem-proving sort of software on it to fill in the holes there that you see in the sketch code, and you get out optimized implementation. So Ross has been looking at that, and tied to that then, what the sketching system allows you to do is generate easily a lot of different, very highly optimized versions of the code. The other thing we then are tying this to is something that does auto-tuning or self-tuning of the code, where you pick from the different implementations which is the best implementation. This picture here is what we call the needle in the haystack picture. It's an old picture from I believe this is from a Sun UltraSpark, but it shows in this case, we're looking at dense matrix multiply, and the question is, what should the block size be? And rather than trying to get an accurate performance model to pick the block size, we just run a whole bunch of different versions. The color here shows you the megaflop rate that you're getting, and the optimal point is this red one down here. I can get my mouse to move down there. We call this the needle in the haystack because there's only one good point in this picture. All the black areas, by the way, are also bad, and that point is very sensitive to the exact block size. So if you pick something that's off just a little bit, you can get significantly worse performance. So because the machines are so unstable in terms of their performance, you have to tune very carefully to them. We think it makes more sense to do this kind of self-tuning and search-based optimization rather than just doing entirely relying on performance models. We have a system called OSCI that also does this for sparse matrices, and that's the basis for the work that I talked about earlier that done by Sam on optimizing sparse matrix vector multiply. And let me just say that this is looking at automatic performance tuning of sparse matrix vector multiply on a number of different matrices here, and the different colors on each of these bars is the different optimizations that were done. The two-core version, which is the green bar, is a kind of a naive parallel code, and what you get when you do all of these other things of auto-tuning are a significant difference in the performance. So the point of this is that auto-tuning is at least as important as parallelism in order to get performance. So we should not be focusing just on parallelism when we're focusing on multi-core. We also have to focus on using the memory system effectively. Sam has also done this for another application called LBMHD, which is a hydrodynamics code. But I want to say then just a few comments about algorithms and why I think we need to rethink the algorithms as well. A lot of algorithms are limited fundamentally by either the memory bandwidth or the communication bandwidth. And the class of algorithms that we're looking at are iterative solvers, specifically Krylov subspace methods. So this is work that I'm doing with Jim Demel and one of his students, Mark Homan, and another student, Margoob. Maya Huden, and these iterative algorithms, the thing that's important about them is a lot of times they're built on top of sparse matrix vector multiply, which itself is limited by the amount of time it takes to read the matrix. So you're limited by memory bandwidth because you're reading the matrix, and you're doing that on every iteration. You're reading the matrix over and over again. If you have divided the matrix up over a number of processors, then you can also be limited by communication latency because you have to send messages in order to do the sparse matrix vector multiply. And there's other communication events that happen inside of these Krylov subspace solvers. So there's some theory that says that we can minimize the network latency costs on a parallel machine and also minimize the memory bandwidth and latency costs on a sequential machine. So avoid memory traffic. And the basic idea is to take these iterative methods and try to run multiple iterative steps in a single read of the matrix. So we read the matrix once and we take multiple iterative steps together. And so we've shown that you can get speed ups for about a 3.2x for an out-of-core implementation of this where the latency is very high. It also looks like it's a good idea on a petascale system that we've built a performance model for. And so the point of this is just that in addition to rethinking the hardware and the software, we also really have to think about the algorithms. In this case, algorithmically, we had this bottleneck, which was very frequent communication between the processors and up and down the memory system. And in this case, we're trying to eliminate that by reorganizing the algorithm. And I'll only say briefly that what happens when you run these algorithms is that you destroy the numerical stability, and you have to get it back again by doing some other numerics, which Jim and his student Mark have worked on. So you change the power kernel inside the Krylov subspace method with a different kernel, and then you get the stability back again. So these are showing different bases that are used inside of the algorithm. So the point of that is that we can't just have architecture people or software people designing these algorithms. We're going to have to bring the actual algorithm designers and the numerical analysts back into the discussion. So to conclude here, I think parallel computing is clearly the future of computer science. We have to rethink the algorithm to design algorithms that make programming easier and design hardware that is going to make it easier to get performance out of the code. Rethink the software so that we take the most advantage of the hardware and makes it easier to do programming. There's a couple of URLs there in case you want to try out our compilers, which are highly portable. And please let me know if you are interested in trying them. Or you could also just download them. And then the last point is that I think we need to include the algorithm designers in this process. So with that, I will stop and see if there are any questions. I'd be happy to take them.
I just wanted to say that if anyone's interested in using UPC, I did install it last year, and I haven't advertised it very well. So
okay, so it's running on your system.
You could use it.
You could use it. And you installed it before or after supercomputing, November?
I think around then.
Around then, okay, because there was a new release that came out for around November, so hopefully, yeah. Eric.
So I think when we discussed this at NSF, the point that Cliff Moeller made was that the hardware will not be made for your problems. The hardware will be made for problems which sells lots of computers.
Right.
So it's made for computer games. We have fancy graphics cards in our computers simply because people play games on the computers, not because we do visualization. So I want you to. I wonder whether you have thought about the hardware.
We'd like to solicit questions from the real side first.
Okay. Oh, that's okay. That's
Okay, I'll answer that one later, but go ahead. Okay.
Go ahead.
Do you have any questions from Duke or UNC? Duke? Oh, ask them to repeat.
Could you use the microphone?
I think he's asking us to repeat the question.
It has been canceled.
I know, your question is...
Use the mic so all the locations can hear us.
Do we have any question from Duke or UNC?
Maybe we can have them to raise their
Question
hand.
from Duke.
Yeah, please go ahead.
Any thoughts, Kathy, about connectivity and data flow when we come to millions of cores or even thousands of cores on the same chip?
So I think the question was about whether I had thought about the connectivity of millions of cores on a chip. I think they are, I mean, there's some obvious things. They're not going to be fully connected. There is going to be some kind of a hierarchy in the machine, even within a chip, which is why I think that looking forward, we maybe get by with something like OpenMP for the next few years on multicore, but in the long run, anything that doesn't help you manage locality is probably not going to be the right solution when you get up to hundreds of cores. So I don't have specific comments about the interconnect, except to say that I don't think it's going to be, not going to be completely flat on a chip.
Any more questions?
So let's take our speaker first, and then we'll go back to the local questions.
I can repeat your
repeat
question.
my question.
Okay, so Eric's question was, you know, why are we talking about influencing the hardware when, of course, the hardware is not going to be designed for scientific computing or high-end computing? It's such a small piece of the market. Instead, the hardware is going to be designed for the mass marketplace. And I agree completely. That's one of the reasons that we were looking at things like the cell architecture, which, of course, is designed for, you know, for games. Now, of course, the fact that the Wii completely took over the PlayStation is sort of a side story in that. But I think we do have to look at where the hardware trends are going to be in the consumer marketplace, and it is one of the reasons that we're looking at things like cell phone processors. But I think there's some hope here, which is that if you look at very sophisticated games, for better or worse, they are basically physics simulations, right? They are not very accurate physics simulations, but they are physics simulations, and therefore even, you know, companies that are putting graphics hardware in are putting in are putting in double precision floating point, which will make them more usable for our purposes. I think the programming model is still going to be a question, and I think that in some cases, like in the case of the original cell processor that I showed you, they did something actually kind of silly in the interface to the double precision floating point unit, which is it wasn't fully pipelined, and I think they thought that they were saving a lot of area or complexity or whatever, and they made it slow. And in fact, it would not have cost them very much to make that a faster double precision unit. So there's some things like this that I think we may be able to influence them. They certainly are going to fix that in the next round of cell, although I'm not sure for the games that double precision floating point is still their limiting factor. But I agree that we have to, you know, we are always sort of at the mercy of the commercial marketplace in terms of trying to build high-end machines out of whatever is highly available.
Hi, just a couple of related questions actually. You showed those graphs of code size of C++ MPI versus your titanium implementation. So the first part is the code size lesser because you have increased language constructs that, like, you know, explode into like a large set of code in C++, or is it because you have better libraries? The second part is, how do the two versions compile down to binaries? Do they compare?
Let's see. You mean the size of the binaries in the terms of the question? Right. I can't really say. So the question was, I think probably people did hear it from the mic, but was about the, well, one of them was about the size of the code that you get out of the C++ and Fortran, and what is the difference between the number of lines of the titanium code versus the C++ and Fortran and MPI code. And first I'd say that they probably compile down to comparable size binaries. Actually, the titanium version is probably significantly larger because it pulls in the Java libraries, and just because of the way on some machines, if we can't do dynamic linking, then we end up with fairly large executables in titanium. But what titanium and UPC both are, in our implementations, are written as source-to-source translators. So you take in titanium or UPC, and there's two completely different compilers, and they translate those into C with calls to GASnet, to this runtime layer. And then from there, you use a C compiler. And that's how we get portability out of them. In terms of the reason for the differences in line count, I think the global address space is part of it. That is, the ability in titanium, in this adaptive mesh refinement example, to say, I want to copy this array to that array, because you can just name both of them, is actually very powerful. You don't have to say, figure out what things go to each other processor and kind of pack them all together and ship them out. And some of that packing, by the way, does happen inside the titanium runtime system, some of those optimizations. So whether it's a library or whether it's part of the language, I mean, the array abstraction is built into the language, in titanium. But I think it's sort of a fuzzy point. It's not as though we're doing a lot of very sophisticated optimizations right now on arrays. We're doing some optimizations. So you could think of it as sort of a built-in library, if you will. There's some optimizations that are important, like bounds checking, that we do. In fact, there's a compiler flag to turn that off in cases where we can't eliminate the bounds checks. So I do think that in the long run, why do you want a compiler versus a library? You want a compiler either because you want some language syntax that makes it more convenient, and so you want something that translates, or you want some optimizations that you can get by doing some analysis, so you either want better performance or better programmability. Yes.
Hi. You'll have to help me with this question a little bit.
Okay.
Let X of t be the most capable computer at time t. Do you have any any thoughts or comments on what graphs would look like, which would be composed of number of persons who know how to effectively use computer X at T, and how many have actually used them to solve problems where it was a useful solution?
Okay, the second one of those I'm going to have to probably hand off to a scientist. But the question is, for a given time t, if you take the fastest machine in the world at that time t, what are the number of programmers that can program it? And it has absolutely declined over time, and I don't know. I can't tell you the exact numbers. I can say that the heart simulation code, one of the reasons we started looking at it was Charlie Peskin said, I don't have any students who want to write MPI programs. Why would why would they waste their time doing that when there's plenty of other applied mathematics they can do? They don't need to waste their time doing that to find interesting thesis topics. And I think there are a lot of application programmers that were already left behind when we moved from vector machines to any kind of a parallel machine. And then some of them came along with some annotations in, say, the compilers, but then we lost them again when we went to MPI. And I think definitely at the high end, there are a very small number of people who actually know how to get useful, very high quality computations on them that are running their codes at an efficient enough level that somebody will let them run on the fastest machine in the world. And then are they doing useful science with them? That I said is a question you have to maybe ask some of the scientists.
Another related question might be how many teachers could teach.
Yeah, this is something that I was actually talking to DOE about, because they said they were thinking about a program to try to take a bunch of Cortex machines, which are these low power, fairly inexpensive parallel machines, and put them out into a bunch of universities. And I said, well, and what are they? And they said they wanted to put them in universities where there was not already a research program in parallel computing, so that there would be more parallel programmers in the world. And I said, well, that's fine, but who's going to teach them to use the parallel machines if you put them into a university where there isn't actually already a faculty member who knows how to teach parallel programming? So there again, I don't know what the exact numbers are. I think it is a big problem. One of the subtleties in some of these languages that, and actually architecture that comes up that we were talking about at a meeting, is the memory consistency model, which is the order in which memory operations appear to take effect. And my claim is this is something that's still kind of something that the languages need to define. And I think for any of these non-trivial models, there are probably at most 2 or 3 people who actually understand this at a deep enough level to actually be able to write correct, high-quality, high-performing code on top of these complicated models. So it is a real danger. I mean, I think we can design a machine that's that's very powerful, but is not programmable by anybody in practice.
There was another, what some people would call 4-letter word that you used, but it shouldn't be a 4-letter word, namely Fortran. But you said Fortran 77. Now that would seem to me to be a 4-letter word.
Well, in fact, I believe that in the Chombo implementation, they do use Fortran 77, because the problem of going from Fortran 77 to Fortran 90 is a little bit like going from Fortran 77 to C++, which is you lose some of the implementation efficiency. And I don't know whether that's because the compiler writers have not put enough effort into Fortran 90 because there's not a big enough market. But Fortran 77 still tends to be, for array-based code, tends to be very efficient. C is very efficient for things that are either unidimensional arrays or kind of pointer-based code, but not for 3D arrays where you're doing anything non-trivial. But yeah.
I also have a related question. So as applications and machines both become larger, automatic performance tuning will be more important and also more challenging. So what do you think about the role of human manual tuning?
So the LBMHD example that I skipped over there, which was looking at this kind of automatic tuning idea pushed up into an application as opposed to done in a little kernel like sparse matrix vector multiply, is the thing that convinced me that we need to rethink what it means to write programs. I think what we should be doing is writing things that are telling some kind of a software system, call it a compiler or whatever you want, how to optimize the code, not writing a particular algorithm in a particular execution that that's going to kind of map in a straightforward way. That in some sense we have to write code that is itself always self-tuning or self-tunable or something like that. And I'm not entirely sure I know what that means, but I think that it means something fairly different than what we're used to. So I don't think it means just writing things in Fortran or C or Java even, and then just sending them through a compiler and having them execute. You know, and a just-in-time compiler is maybe a step in the right direction, but I don't think that probably goes far enough either in the performance direction. So I think we really need to completely rethink the way we write software.
Let's thank the speaker.